So anyways, if there's any questions, holler at me. Otherwise, let's start working through some example questions. So I tried to do some questions that kind of look like the ones that might be on the test. So first one says, how many milliliters of lidocaine supplied as a 5% injectable and how much glycerin with a specific gravity of 1.2 would be required to prepare the following ophthalmic solution. So if you look on the prescription, it wants lidocaine as your active therapeutic agent at 3.5%. So we know exactly how much lidocaine has to be in there to be therapeutic. Then it said add as much ever glycerin and water as you need to get QSAD, meaning to a total volume of 30 milliliters. And the amount of glycerin you're going to need is the amount that it takes to make it isotonic. Okay, so we know how much lidocaine has to be in there, and we're going to have to figure out how much glycerin we have to add to make it isotonic. And in this method, what method is this? Looking at what I provided you in the prescription? The delta and the T's and the F, that's the freezing point depression method. So that's the method we're going to use to do that. I would tell you, though, you don't even have to worry about the isotonicity to answer the first question. The first question was how many milliliters of the lidocaine? Because the amount of lidocaine is the amount it needs to be therapeutic. And it told us 3.5%, so let's do that one right away. So again, we're making 30 milliliters, so let's take 30 milliliters times the concentration in the prescription, right? It told us 3.5%. So again, and we're making 30 milliliters, so that's that. So to make 30 milliliters be 3.5%, you multiply that so that the milliliters cancel and you're in grams of lidocaine. And then the last step is, well, what is our source of lidocaine? We're not just weighing it, we're getting it from a 5% injectable. So 5% injectable means 5 grams and 100 mils, but let's set it up so that if we multiply by 100 mils over 5 grams, grams of lidocaine cancel, and you get milliliters of that injectable. So to give enough lidocaine so that we make our 30 mils to be 3.5%, we have to use 21 milliliters of the injectable lidocaine. 21 milliliters of the injectable lidocaine provides us the amount of lidocaine we need in our ophthalmic solution. Any questions with that? Okay. Now, let's deal with the isotonicity, okay? Because here's the deal. Is that amount of lidocaine enough to make the product isotonic? Well, let's even answer that question, because we're going to have lidocaine in there, so we know it's going to contribute to the isotonicity or the tonicity to some extent. So let's use this information. So again, maybe I'll switch over to green just because I like color so much. So there's what I know about lidocaine, all right? So I'm going to pull that information down to here and re-express it, because the delta TF 1% means a 1% concentration of that solution lowers the freezing point by those numbered degrees Celsius. So let's set that equal to 0.063 degrees Celsius over 1% lidocaine. Are you all okay with this? This isn't critical. To use the freezing point depression method, you have to use those delta TF values and set up the right proportion. Because I know for a 1% lidocaine, I will reduce the freezing point by 0.063 degrees. Right? I can set that equal to, well, I'm not going to do 1% lidocaine. What percent lidocaine am I doing? 3.5%. So let's put some X over 3.5%. X is the degree reduction I will get when I use a 3.5% amount of lidocaine. So it will proportion it for me. So if I solve for X by just multiplying 0.063 times 3.5, I get a 0.22 degrees Celsius reduction from just the lidocaine. Is that enough? You guys remember what the target is, and what does an isotonic solution freeze at? It freezes at negative what? 0.52. So our target is 0.52. So what we need to do is start with our target here, subtract what we're getting from the lidocaine, and whatever is left over needs to come from what? What are we using in our prescription? Glycerin. So if we subtract 0.5, or from 0.52, we subtract our 0.2 that's going to come from the lidocaine, the difference is 0.3. That's what we need to get from our glycerin, all right? So let's, again, circle our glycerin here. So here's the delta TF for the glycerin. So let's bring it down, set it up the same way we did before. That value means 0.2 degrees Celsius for every 1% concentration of glycerin. Set that equal to, now we know our target, though. Our target now for the glycerin is the difference. So we're going to put 0.3 degrees Celsius on top and solve for X. And now X will be the percent strength of glycerin that gives us 0.3 degrees Celsius reduction, which is what we need to add to our lidocaine. So if we solve for X now, what we get is 1.5, and again, it's 1.5% glycerin. So we're almost done, but it wanted to know the volume of glycerin, just not the concentration. So the next step is to take our percent glycerin here, re-express it here, and remember we want 30 milliliters. So if I have 30 milliliters times the 1.5%, meaning 1.5 grams per 100 mils, then again, milliliters will cancel, and I will be in grams of glycerin, and I get 0.45 grams of glycerin. And we're almost done. But the problem is we're going to measure that by volume. So again, we were given the specific gravity. So the specific gravity for glycerin is 1.25 grams per mil. So if we want to convert its weight to a volume, we're going to take the 0.45 grams times 1 mil over 1.25, so that grams cancel. And you do that final division there, and you get a final volume of glycerin of 0.36. Okay? And so that's our big final answer to that one. Is that okay? Let's do the same kind of thing, but now in a very different way, using the sodium chloride equivalent method. So in this prescription, it wants to know how many milliliters of a boric acid solution. All we're using boric acid for in this example is to make the solution isotonic, all right? So what is our active ingredient? Oxymetazolone. So that's the drug, that's the vasoconstrictor we want in this solution, and it needs to be therapeutically at a concentration of 0.5%. So that's the amount of oxymetazolone I have to use. Then I'm going to use whatever amount, whatever volume of this boric acid solution, so that my final product is isotonic, and again, has a final total volume of 15 milliliters, all right? So, but now instead of delta TF, I've given you E. So do you remember what that means? That's important for these questions. E is the sodium chloride equivalent. E stands for equivalent. So for example, for oxymetazolone, 0.2 means what? 0.2 grams of sodium chloride per gram of oxymetazolone. Remember how to set up those E values. Okay, and you'll see that here in a second, but that's the trick, the memory. The other thing you got to do when you start with the sodium chloride equivalent methods is start by calculating the weight of your active ingredient. And again, it's defined. I know I want 0.5% of oxymetazolone, and I'm making 15 mils. So let's start with my 15 mils here. Bring that over to here. And again, this is my percent I want. I know that. So let's calculate the weight of oxymetazolone I need. 15 mils times 0.5 grams per 100 mils. Mils cancel, and I'm in grams of oxymetazolone. Easy breezy. That is the weight of oxymetazolone I have to use. Okay, I'm going to use that. How much sodium chloride does that weight of oxymetazolone mimic? How much sodium chloride is that the same as if we had used sodium chloride? So let's convert it from the weight of oxymetazolone to an equivalent weight of sodium chloride. That's where this E value comes in. So now I'm going to use the E value, take the same answer and just continue on and take the 0.075 grams of oxymetazolone times its E value expressed as 0.2 grams of sodium chloride per gram of drug. That's why I emphasize that, because now grams of drug cancel, and what I have now is a weight, 0.015 grams of sodium chloride. Is that sodium chloride actually in the oxymetazolone? No, it's an equivalent amount. It's saying that that's the amount of sodium chloride that amount of oxymetazolone mimics osmotically, all right? So now I have an equivalent amount of sodium chloride. The next question is, how much sodium chloride do you need? This is something you should be able to answer in general. If I said for 100 milliliters, would you know how much sodium chloride you need? You better. It's what? 0.9, right? Because it's 0.9%, 0.9 grams per 100 milliliters, because that's what we're going to start with. So this is the knowledge you have. And again, what we're trying to make, though, is not 100 mils. We want 15 mils. So let's just set up a proportion. 0.9 grams of sodium chloride over 100 mils would be the same as how much sodium chloride over, what are we making? 15 mils. So set it over 15 mils. You solve for that, and that tells you your target. That says for 15 milliliters, the amount of sodium chloride you would need to make it isotonic is 0.135. Okay? So that's our target. So let's start with our target, subtract the amount from our oxymetazolone. So that's the amount I'm going to get from my active ingredient. And lo and behold, when I subtract those, I see that I still need some more sodium chloride. I still need 0.12 grams of sodium chloride equivalent to make this isotonic. Am I going to use sodium chloride to get it? No. What am I using? Boric acid. So this might be a little trick for some of you. You can now, once you go from sodium chloride, you can go to the amount of drug that amount of sodium chloride would mimic. Let's use the E value for the boric acid. Come down here, and express it, though, as the fact that an E value of 0.52 means 0.52 grams of sodium chloride per gram of boric acid, well, we can set 1 gram of boric acid on top over 0.52 grams of sodium chloride. That way, when we multiply by the amount that we're still trying to obtain, grams of sodium chloride cancel, and that would tell me the weight of boric acid I need to give that equivalent amount of sodium chloride. The last step, though, is to go from the grams of boric acid to the volume, since we're using a what percent solution? 5% solution. So the last step is to multiply the weight times 100 mils over 5 grams, since that's 5%. That way grams of boric acid cancel, and I get a final volume, and this was my final answer here, would be 4.6 mils at that 5% boric acid solution. Happy? Sad? Okay? Indifferent? Let's do it. Okay, that was my review on isotonicity. We've done the sort of chloride equivalent method. We've done the freezing point depression method. Okay? Those are on the test. Make sure you can do some variation of those kind of prescriptions and drugs and E-values and all that and come up and do what I did. All right, let's move on and practice a little bit with the milliequivalents. So we got milligrams to millimoles to milliequivalents and milliosmoles. So that's kind of what we're going to work on here a little bit. This question says a hospitalized patient needs 16 milliequivalents of magnesium to be administered intravenously. How many milliliters of a 20% weight per volume, and again, weight per volume means grams per 100 mils, of magnesium chloride hexahydrate solution will be needed to supply this dose? What was the dose? What's our target? What are we trying to get? Realize this is what we're trying to prepare. So that's where you start this question. Start with the dose of 16 milliequivalents. What are we trying to get to? We're going to eventually have to get to milliliters of solution that's in a weight per volume. So we obviously got to go from milliequivalents to millimoles, and then millimoles to milligrams, and then to volume. I'm just trying to, if you think about the roadmap, those are going to be all of our unit conversions. So I start by converting and getting rid of milliequivalents by converting it back to the number of molecules, if you will, of magnesium. So, and you do that by dividing it by the valence. So again, the valence on magnesium is 2, so there are 2 milliequivalents of magnesium for every 1 millimole. So that's where the 2 on the bottom comes from. Is everyone okay with that? The valence number goes with the milliequivalent. So there are valence on magnesium is 2, so 2 milliequivalents for every 1 millimole. Now I'm in millimoles of magnesium. I next need to convert to the number of molecules of magnesium chloride. So I have to look at the molecule. MgCl2 has 1 magnesium for every 1 MgCl2. So it's a 1-to-1. So now when I multiply like this, I can convert from my millimoles of magnesium to just millimoles of magnesium chloride. All right? Now I'm going to convert that to the weight of my product. And remember, the weight of my product is magnesium chloride hexahydrate, so I have to use the molecular weight for that. And if I multiply by 203 milligrams of magnesium chloride hexahydrate per millimole, then that cancels out my millimoles, and I'm now in the weight of the magnesium chloride. And I'm almost there, right? But I got to get in the same units. I'm in milligrams. So my next step was to convert milligrams to grams, so nothing new there. And then lastly, why did I convert to grams? Because my 20% weight per volume means 20 grams per 100 milliliters. So now I'm in grams. I can multiply by 100 mils over 20 grams, so the grams cancel, and my final units are milliliters. If you do that math all the way across, you should get 8.12 milliliters. So this is a good example. It was a long road, right? We had to convert all the way from lots of different things. Is there any step in there that you don't follow? That's what you got to ask yourself. Did I not understand that proportion or that step from converting this to this and this to this? Okay? A lot of you can sometimes skip steps because if it's a 1-to-1, you mathematically don't change anything, but that's what leads to a lot of errors. So I highly recommend for these that you take your time and write out the units and convert one step at a time, or something could go wrong. All right, let's read the next question first. So it follows up on this. So we've got this 8.12 milliliters that provides 16 milliequivalents. What we're going to do is put that in an IV bag such that the final volume is 1,000 milliliters. So don't worry about the excess. It's just a total volume of 1,000 milliliters, 1 liter, and we're using D5W. What does D5 stand for? 5% dextrose, or dextrose 5%. So again, and so we're putting our magnesium in D5W and basically asking what would the final osmolarity of that solution be. So instead of milliequivalents, we're talking about osmolarity, or milliosmoles. Can we do it? We can do it. What would provide osmotic strength in that formulation? Does the dextrose have any osmotic effects? Yes, so we got to take care of the dextrose. Will the magnesium chloride have some osmotic effect? Yes, so we got to do one at a time. So let's start with the magnesium chloride. Do I know how much magnesium chloride is going to be in there? Yeah, I'm adding 16 milliequivalents. But I've got to go from the milliequivalents because that's about chemical activity. That's charge. I don't care about charge. I need molecules. So let's convert from the amount of electrical energy to the number of molecules, again, by taking the 16 MEQs times the fact that there's 1 millimole of magnesium for every 2 milliequivalents because of the valence. Then this is where I'm going to be complete and step back from just millimoles of magnesium to the number of molecules of magnesium chloride, which again is 1 to 1, but I'm now in my millimoles of magnesium chloride. Take a minute and look at the formula. Is magnesium chloride an electrolyte? Will it dissociate? Yes, it will dissociate into how many particles? 1 magnesium and how many chlorides? 2 chlorides. So total would be 3. So there are 3 milliosmoles for every 1 millimole. So I'm telling you, this is an important step here in the idea when you're doing with your milliosmoles. So that converts from molecules to milliosmoles, and if I do that math, I get 24. Is that the answer to this question? Or did we forget about something? We forgot about the dextrose, man. So let's do the dextrose. We got to account for that. So I know it's 5%, so I got to start back with, well, what's my total volume? We said the total volume is going to be a liter, which is 1,000 milliliters. So I take 1,000 milliliters times 5%, which is 5 grams per 100 milliliters. So my milliliters cancel. Now let's just convert from grams to milligrams by multiplying by 1,000. Now I can convert to the number of molecules by taking my weight and dividing it by the formula weight, which I gave you here was 198. So that divides out the milligrams. Now I'm in molecules. That's where I need to be, man. So what happens when you put a dextrose into water? How many particles do you get then? Does it dissociate? No, dextrose does not dissociate. It's a non-electrolyte, so you get 1 molecule for every 1, and you get 1 milliosmole for every 1 molecule, so it's 1 to 1. So again, you cross that straight over, and you end up getting 253 milliosmoles. So clearly, what we're going to have to do on the final step is just add it all together. So the 24 plus the 253 means we would have a total of 277 milliosmoles. But it wanted osmolarity, which is milliosmoles per what? Per liter. But what did we start with here? A liter. So we're in a liter. So again, essentially our 277 milliosmoles is the number of milliosmoles per liter, which is osmolarity. Okay? Let's keep it going. All right, so this is going a little bit using our milliequivalents and doing our chapter 13 kind of IV infusion questions, because it says, if a liter of this solution is to be administered over 4 hours, using an administration set with a drop factor of 20 drops per milliliter, what would be the infusion rate in drops per minute? So really make sure you got a couple of things here. We have drops per minute is our target. We have drops per hour, and we have 1 liter of solution going in over 4 hours. Okay? That's why sometimes these questions can be a little bit difficult, because there's a lot of information there. But let's start with the thing to be infused. We have an IV, right? What is the volume of the IV we're trying to administer? 1 liter. What amount of time does that have to go in over? 1 liter has to go in over 4 hours. That's what we're starting with, okay? So realize that's where you would start. And I went ahead and changed my 1 liter to 1,000 milliliters. Hopefully that doesn't throw anyone off. But really, we have 1,000 milliliters in 4 hours. That's an infusion rate. If you divide that out, that would be in milliliters per hour. That's a very common infusion rate. The problem here is we don't want the rate in mils per hour. What is our final target? Drops per minute. So we have to convert mils to drops and hours to minutes. That's all the trick is to this question. So you can do either one in any order, but once you set this up, that's where we started with, then again, I'm going to convert my volume to drops, since again, I know that it's a 20 drop per mil set. If I multiply by 20 drops per mil, then my mils cancel and I'm in drops. Lastly, since I don't want hours, I want minutes, I'm going to multiply with the fact that in 1 hour there are 60 minutes, so that again, I can see if I do my math right, then I will have my final units in drops per minute. If I do my math, I get 83 drops per minute. Okay? All right, let's do, oh, Larry, got to read the question. Sorry, I get so excited. This patient, now, okay, so here's the deal. Patient survived your treatment, so they're going home. Yay. Will they have IV access at home? No, but they still need to get some magnesium supplements. So let's use the Mag-Ox tablets. They're Mag-Ox are 400 milligram tablets. The dose the doctor wants this patient to get every single day is 30 milliequivalents of magnesium. So all we got to do is take their target, which is 30 milliequivalents, and convert it to the number of these MagOx tablets to provide it. Easy breezy. Same sort of thing. This is a great example, again, of your unit conversion stuff. So let's start with our target, which, again, we wanted 30 milliequivalents, so that's what I'm starting with. I got to convert from milliequivalents to molecules. So let's multiply by 1 millimole per 2 milliequivalents, since the valence is 2. That cancels out milliequivalents. Let's convert from the number of molecules of magnesium to the number of molecules of magnesium oxide, because the formula is MgO. So 1 magnesium for every 1 magnesium oxide. So now I'm in magnesium oxide molecules. Let's convert to the weight of those molecules by multiplying by its formula weight, which was 40 given to us. So now I'm in the weight of magnesium oxide. But I want to know the number of tablets. So let's just go one more step, and the ratio is, what was the strength of magnesium per tablet? We said 400 milligrams of magnesium for each tablet, okay? So that's what I'm going to set it up as, 1 tablet over 400 milligrams, so that my milligrams of magnesium oxide cancel. And again, my final remaining unit would be tablet. So if you do that math all the way across, you get 1.5 tablets. Okay? And can some tablets be broken because they're scored in half? Absolutely. So we break one of them and take 1.5 every single day. All right, you ready to move on? Oh yeah, baby, let's do some dilution, right? Those CQs and CQs, we love this. This is awesome. So it's not a double D, it's a single D, so we'll just do a single dilution, but it's set up a little bit like that. So let's see, this one can be a little bit hard, I think, sometimes. So let's see. The prescription is kind of written weird. It says potassium permanganate solution, and again, that's kind of an antiseptic in solution. We want 90 mils of that. So we know the volume. I want to make 90 mils of this potassium permanganate solution. Well, what's the concentration? Well, I was mean. I didn't give you a concentration, but I told you that it has to have a concentration such that what? Such that 1 teaspoonful of that liquid, with diluted to a liter, gives you a 1 to 20,000 concentration. Okay? So I didn't tell you the concentration, but I told you a way to be able to determine the concentration. Okay? So here's the deal. This last solution that has 1 liter and 1 to 20,000 concentration, what's the source of that drug? The only mass of potassium permanganate will come from my 5 milliliters of solution. So this is a dilution. It's going from my initial concentration that I'm trying to solve to this final concentration. And I know this final concentration. So this is a CQ equals CQ. So let's just set those up. What is the concentration I'm starting with? I don't know. That's X. That's what we're solving for. I don't know what the initial concentration is. And I'll come back to the units here in a minute. What is the quantity? How much of that initial solution did it tell me that I would dilute? A teaspoonful. And you all remember the metric volume for a teaspoonful is how much? 5 milliliters. So again, I cheated there a little bit and just set my quantity 1 equal to 5 milliliters. I'm taking a teaspoonful, which is 5 milliliters, of some unknown concentration. That's C1 and Q1. What do I get in the end? Do I know what my final concentration is going to be? Yes, it's 1 to 20,000. And I look at this. I didn't even do the math here. I'm just leaving it that way. And you could go ahead and divide it out, but it's a teeny number, so I just left it like that. So my concentration from the question is 1 to 20,000. And what are the units? Weight per volume, right? So it's grams per milliliter. So it's a 1 to 20,000 grams per milliliter. That's the concentration in the end. Do I know what my final quantity will be when I make it? 1,000 milliliters. So I know my Q2 and I know my C2. All right. Now, so we want to do our unit check here. So that unit matches that unit. I have this unit, so I'm going to go ahead and assign my X equal to the concentration in grams per mil. Okay. So that's why I set it up that way, because I need to make them match. All right. So my quantity 1, or I should say my concentration 1, means X grams per mil. So let's just do the, so if you do your mass, then it's that concentration times that quantity for the beginning, and it's that concentration times that quantity for the end. And again, we know M1 equals M2, so let's just carry them down here. So on the left, we have X times 5, and on the right, we have 1 over 20,000 times 1,000. Okay, but we use calculators so big numbers don't scare us, right? So no problem with that. So on the left, 5 times X is 5X. What is 1,000 divided by 20,000? 0.05. It works out, 0.05. So 5X equals 0.05. Divide each side by 5, and X equals 0.01. What are the units, though? Remember, we got to go back and follow our units down. We set them up, and they had to match, so that had to match that. That's why we chose that. So in the end, my X equals 0.01 grams per milliliter. And X equals the what? What was X? The concentration of our initial solution that we're going to use 5 mils from. So is that the answer to the question? Almost. We had to get that, but we got to go one step further. It wants to know how many grams of potassium permanganate. Do we know how much solution we need to make in the prescription? Yeah, we need to make 90 milliliters of a solution that has that concentration. So let's just use that. So I use my 90 milliliters times that concentration, set up so that my milliliters cancel, and if you take 90 times 0.01 grams per mil, mils cancel, you get 0.9 grams of potassium permanganate. That's what you would need to make that 90 mil solution have the concentration you need. Are we okay on that one? It's a little tricky. I understand that, but it's a key thing. But do you see the process of setting up the C1, Q1, C2, Q2, and looking at the units and trying to get those settled first? A lot of the questions I gave you, you had to change a concentration from grams per mil to percent, or from percent to something else. But do that work first and set up your C's and Q's equal C's and Q's, but in the same units. Then you can just do the algebra and get your answer and be happy. Okay? All right, let's do another one, a little variation. It says an insect venom concentrate for immunotherapy. Basically, this one is somebody who's getting shots to reduce their allergic reaction to bee stings. All right, so this is the kind of venom we would inject into them so that they learn and develop a resistance to being so reactive to a bee sting. So anyway, that venom concentrate that we have comes as 100 micrograms per milliliter. That's the stock concentration. What we want to know is how many milliliters of water should be added to 1.2 mils of that venom such that our final concentration ends up being a 1 to 100,000 dilution. All right? So I tried to set this one up in a slightly different way to see how this works for you. So here's the deal. Where do we start with this? Well, we need a final concentration, which is a weight per volume. We need a weight of our venom. All right? So we've got to get there eventually. Well, what will determine how much is in our thing is the amount that we start with. We're starting with 1.2 milliliters of this venom, and it has a concentration. So let's start with the volume of that venom concentrate, and then multiply it times its concentration. What was its concentration? We said it was 100 milligrams per milliliter. Micrograms, sorry. So 100 micrograms per milliliter. So if I multiply those two out, then would you agree, if I started with 1.2 mils and I multiply something that's got 100 micrograms per milliliter, can you do that simple math? How many micrograms do we have to begin with? 1,200? All right, so we have 1,200 micrograms to begin with because I have 1.2 mils of 100 micrograms per mil. Okay, so very good. I said that wrong, didn't I? It's 120. So it's 100 anyway. So my quick mental math. All right. I'm going to shut up. Let's just use my values here so I don't mess anyone up. I start with 1.2 mils times 100 micrograms per milliliter. So I'm in micrograms. The problem here is, what are the units of this concentration? Grams per milliliter, right? Hopefully you got that. So I'm going to need to get to grams. So all I'm doing here is converting micrograms to milligrams because I can only go by 1,000 at a time. So now I'm in milligrams. Now I'm going to go from milligrams to grams by, again, dividing by 1,000. So now I'm finally in grams. And now I can finally say, if that's the weight of this venom I have, to get the right volume, at a 1 to 100,000 dilution, I'm going to multiply by that concentration as 100,000 mils over 1 gram, so that my grams cancel, my final units are mils, and if you do that math, the final answer is 12 milliliters. All right? Here's the one trick I would say about this question. That's the total volume. So the total weight or amount of the immunotherapy has to be in what total volume? 12 milliliters. The question wants to know how much water to add. So are you going to add 12 milliliters of water? No, because what is the volume of the venom? The venom is 1.2 mils in itself. So the trick you have to remember is that you're going to start with your total here and subtract the amount of the venom, and the remaining is the amount of water. So the amount of water to add to the 1.2 mils of venom is 10.8. 10.8 plus 1.2 gives a total of 12 milliliters to give you the total correct volume. Do you see where that was a little bit of a trick there at the end to remember what you're solving for is the total volume, and you have to subtract out the volume from the active source of your drug. All right. All right, let's get to another algebra method. So let's do another dilution, all right, with a little bit of a trick. I like this trick. It says, how many milliliters of a 28% weight per weight strong ammonia, having a specific gravity of 0.89, should be used to prepare 2,000 milliliters of a 10% weight per weight ammonia solution with its specific gravity? This is just a dilution. We need to take one concentration and some volume to make a different concentration and a final volume, right? It's a simple dilution question. The only trick here is this, the fact that I have a total volume that I want to make, but I'm dealing with a weight per weight percentage. So those units don't match, okay? So you could either try to change your weight per weight concentrations to weight per volumes, or you can change your volumes to weights. All right, you could do this either way. It made more sense to me just to change my target, because here's the deal. It says my target I want to make is 2,000 milliliters. I could just call that a weight, right? Wouldn't 2,000 mils in volume weigh a certain amount? And I have the specific gravity, so I think the easiest way to approach this question is let's just redo this, and instead of volume, let's convert it to a weight. Since it has a specific gravity of 0.96, I can just take the volume, 2,000 mils, times 0.96 grams per mil, mils cancel, and really what I'm saying is what I want to make in the end is 1,920 grams of solution. I can handle that. I'm in grams, and my weight and my percent's in weight per weight, which is grams. So that's good. Now let's just set up our C's and Q's, all right? So what are we starting with? We're starting with a 28%, so this is what it wants to know, 28%, so that's my starting concentration. And it wants to know how many milliliters. But remember, we've still got this volume issue here. So instead of how many milliliters, we really are going to start off by finding how many grams. We'll come back and answer that in the end. But realize we don't know it, so it's still X, but I used grams as my units here. So don't forget about that when we solve this. All right, so 28% concentration, weight per weight, is my C, and my Q is some X amount of grams. What am I going to get at the end? What's my C2? Well, my C2 is 10% weight per weight. And what is my Q2? Well, remember, that's why we converted it already. My Q2, I know, is 1,920 grams. So it's pretty straightforward. Since mass 1 equals mass 2, I can say that 28% times X grams is going to equal my 10% times my 1,920 grams. All right? So let's do a unit check here, percent, grams, and grams. So I can drop the units and just solve. 28 times X is 28X, equals 10 times 1,920 is 19,200. I divide both sides by 28, and I find that X equals 685.7 grams. That truly is the amount of my 28% concentration that I need. But the question did ask for the final what? Milliliters. It wanted the final volume. So my last step is simply to take that target weight and use its specific gravity, which is a different specific gravity. But I now need to use it so that I can convert from a weight to a volume. So I'm going to multiply by 1 milliliter over 0.89 grams, so that grams cancel. And if you do that math, your final volume that equals the same amount of weight would be 770 milliliters. Okay? So did the C's and the Q's work the same way? Yes. This was just a little bit of a trick question in that we needed to get either all into volume or all into weight. It was easier to get into weight to be able to solve it. So we used our specific gravities, which is an important thing to be able to do, to convert volumes to weights. And then finally, our weight back to a volume. Okay? All right, let's do an easy alligation. This one's easy. I like this one because if you struggle with this one, you've got to go back and review this. These are alligation questions are pretty straightforward. It says you want to prepare 250 mils of a solution containing 40% dextrose. That's your target, 250 mils of 40% dextrose. You have 50% and you have 20%. So how much of each one are you going to use to mix them together? Does that sound like an alligation question? We've done enough of those that should spring to your mind, ooh, that's an alligation thing. It's a high and a low and I want something in the middle. Let's set it up. All right, so I will tell you to put the high on top, so there's my high, and then you put your low on the bottom, there's my low, and what I want in the middle, my target is in the middle to the right, okay? So remember, cross subtract, so starting from the top left, the 50, going down to the lower right, take 50 minus 40 and get 10. Remember to drop the units, you're in parts. So 50 minus 40 is 10, so 10 is directly across from the 20%. Diagonally going from the bottom left up to the upper right, take 40 minus 20, follow up, and you get 20, all right? Then I would remind you to remember that the 20 parts here refers to the 50%, Okay? The 10 parts here will represent the 20%. And again, the total number of parts, which you have to add together, I kind of skipped that step, but remember, if you add 20 plus 10 together, you get 30. So again, the 30 parts represents the total that we're trying to compound, which is the 40%. Okay? Can you get to that pretty quickly? Now, the question is, where do we go from here? What else do we know? We want to produce 250 mils of what? The final product. That's what I want in the end. What is the final concentration? 40%. So I want 250 mils of 40%. So this 250 mils represents the 40%. That represents this, so that equals both of those 30 parts. So all we can do is set those proportions equal to x over the total, which is 250 mils. The 250 mils represents the 30 parts. So that's going to be the same for both my 50% and my 20%. So I set up those proportions, 20 over 30 on top equals x over 250. So if I solve for that, then again, this x here represents the 50, so that gives me the 166.7. Do the same thing down on the bottom for the 20%. The ratio is 10 over 30 equals x over 250. Solve for x, and you get 83.3. What is 83.3 plus 166.7? 250. Those two added together will give you the total volume you want, and now it proportions them in the right way so that when they are mixed together, your final concentration is 40%. Okay? This is a good example of what I would call a fairly straightforward alligation. Okay? So let's do a little more difficult one. Okay? Kind of works the same way, but these are where the problems can be more difficult than that, I think, more straightforward one. Here we go. It says, how many grams of a 20% weight per weight zinc oxide ointment should be added to change this prescription to a 12.5%? All right? So we have a high strength, 20%, and we want a 12.5%. So I guess my first question to you is, what percent of zinc oxide is in this prescription? Did it tell it to us in the prescription? No. So we're going to have to figure it out. Our first step here would be to know, what is our starting concentration? I know I want a target of 12.5, and I know I'm going to use a 20 in this ointment, but I don't know what this ointment is. It's got what zinc oxide, how much zinc oxide is in there? And I love this question because you don't get rid of me at the end of this semester. You remember, I come back next semester, and what do we do next semester? Compound. We will make a cream and an ointment just like this. And the nice thing is you actually make it, not just talk about it, thank God. But you still have to be able to do these calculations. That's why I think this is important. So this also gets to interpreting this prescription. So let me ask you this. This is a little tricky on this. How much petrolatum? What is the total amount of petrolatum we're adding? Is it 60 grams, or will the total weight of everything be 60 grams? So that's where you got to use your interpretation. Remember, that just says petrolatum 60 grams. If the total weight was going to be 60 grams, what was the Latin abbreviations for that we've seen this semester? QSAD, which means up to a total of 60 grams. That's not on there. So how much petrolatum are we using here? 60 grams. We're going to use 60 grams of petrolatum. What does AA? Remember, see where it says zinc oxide calamine with a line AA, 2.2 grams. Does that mean the two of those together add up to 2.2 grams? AA stands for each. Okay, so that is basically saying zinc oxide, 2.2 grams, calamine, 2.2 grams. Each of those are 2.2 grams. That interpretation is absolutely necessary to be able to calculate the correct percentage of zinc oxide in the initial compound. Let's do that. To calculate the initial concentration, we need to know the total weight. And we said the total weight is going to be the 2.2 grams of zinc oxide, plus the 2.2 grams of the calamine, plus the 60 grams of the petrolatum. Just add those things together. Would you agree? 2.2 plus 2.2 plus 60 is 64.4. So when we mish all that stuff together next semester, your total weight of that ointment would be 64.4 grams. But what would the concentration of zinc oxide of that concentration be? Well, it would be 2.2 grams over 64.4. Okay, so is everyone okay with this? That is the concentration of zinc oxide in our product. But I need to know the percent, and you could have done this a couple of different ways. But I just set it equal to x over 100 grams. And if you solve for x now, that would be the weight in grams. That would be make 100 grams have the same concentration. So if you solve for that, you get 3.4. That's 3.4 grams per 100 grams. That's 3.4%. You with me? So what I basically did is use this total weight here, okay, down there, take the weight of just the zinc oxide, okay, and divide that out and proportion it out to be a percent. So it's 3.4. So now does it make sense? What is our high strength? 20%. What are we adding it to? What's the low strength? 3.4%. And what are we trying to make? 12.5%. So let's set up our alligation. All right, so starting on the top 20, going diagonally down, let's subtract the 12.5, keep it going down. 20 minus 12.5 is 7.5. Starting with our low strength 3.4, going up to the upper right, 12.5 minus 3.4 gives us 9.1. So I'll remind you, let's see if I get this right. 20% goes with 9.1. 3.4% goes to the 7.5. And the 16.6 combined, and I skipped that little step about adding those together, but if you add those two together, then the combined total parts would be 16.6, represents the final product that we're trying to make. Okay? Because now I guess the question is, where do we go from here? I got all the proportions. You've got the right proportions for the two ingredients. How do we actually determine a weight? What is the one weight? We only know one weight. What is the one weight we know? Do we know how much of that original formulation we're going to make? How much? What do we calculate the total weight to be? 64.4, right? What I'm trying to say here is what we know, and I probably should use blue here. No, let's use red. What I know is that I'm going to have 64.4 grams of an ointment that has 3.4% concentration. Are you okay with that? Do you see where the 64? That's the amount that we have. That amount is the amount of the 3.4%. Therefore, that amount represents the 7.5 parts. So where you go from this is to set that ratio, 7.5 over 16.6, equal to 64.4 grams, since that's the weight of the 3.4% ointment we have, over X. And what we're solving for is the total. It's over the 16.6 parts, right? That represented the total weight. So now if I solve for X, you're solving for the total weight of the compound. So if you do that math, 16.6 times 64.4 divided by 7.5, you get 142.5 grams, right? That's the total weight of the combination. The combination of what two things? The 3.4% and the 20%. So it's not our final answer yet. Could you just subtract these two and get the answer? Yes, but Larry doesn't like that. That's too easy. All right, so I want to make sure you understand now this idea here. This 142.5 represents what parts? The 16.6 parts. Does that make sense? The total weight had 16.6 parts. And since that's the same total weight as that 16.6 parts, what I can do is use the upper formula now to say that 9.1 over 16.6 is equal to X over 142.5, because I now know that 16.6 parts represents 142.5. Solve for X, and you do get then the weight of the 20%, which is 78. And I know you probably won't solve it that way, but sometimes you may have to, anyway, start one place or the other. What's important is that you can identify these ratios and the according weights. And again, the weight that we had, the 64.4, represented the 7.5 parts of the 3.4%. That's how you could actually then go ahead and solve that question. So, all right. Any issues with that? All right, the last question, we're almost done, is an easy one. It's really, really repetitive because I had to decide this. It's like, okay, what have I thought you guys have struggled with more? I thought you were going to have more problems with the allegations and the algebra. You guys seem to be doing really well with that. The place you have consistently, as a whole, I'm not pointing at anyone individually, as a group though, has struggled with the Milliequivalents. So what I did is come up with a question to make you just calculate Milliequivalents and Milliequivalents and Milliequivalents and Milliequivalents, and also milliosmoles, since again that's kind of a related idea. So the idea behind this is there is this commercial product. You're actually going to see here in the end, we're going to calculate this commercial's product's ingredients and how many milliequivalents of each of those ingredients are provided when you inject a dose or basically use this 20 milliliter bottle. So I give you the formula there for each of those ingredients, and I ask you to calculate the milliequivalents of each electrolyte. Okay? In the end, does it matter whether the sodium comes from the sodium chloride or the sodium acetate? No, we're going to add up similar electrolytes and give you total amounts of sodiums and total chlorides and total those. So it's a little bit involved in that sense, but the easiest way to do this is one step at a time. So the first thing I would do is let's start with the sodium chloride. We are starting with 322 milligrams of that sodium chloride. All right, so that comes from there. So let's convert it to milliequivalents. So the first step is to convert the weight in milligrams to the number of millimoles by dividing by the formula weight. Right? That converts it to the number of millimoles. Everyone do that okay? All right. Now, you can do this in any order you want. I went ahead and let's go ahead and first calculate, since I got molecules there, let's go ahead and calculate the osmolarity, or let's calculate the milliosmoles. Because when sodium chloride dissociates, how many particles are left? 2, right? It's 1 sodium, 1 chloride. So there are 2 milliosmoles per every 1 millimole. So if I multiply that against that, that gives me my milliosmoles for the sodium chloride is 11. So I get 11 milliosmoles from that amount of sodium chloride. Then I can take this same amount here and use it to both calculate the amount of sodium and the amount of chloride. You get both sodium and chloride. So how many milliequivalents of each of those? Well, I started with 5.5 millimoles. There's 1 molecule of sodium for every 1 sodium chloride, and the valence on sodium is 1. Remember, so there's where the valence comes from for both of those. The valence is 1, so it's 1 to 1. So 5.5 millimoles of sodium chloride give you 5.5 milliequivalents of sodium. They also give you 5.5 milliequivalents of chloride. Would you have known to get both of those numbers? Remember, if I'm wanting to know the total amount of electrolytes, I can get a milliequivalents of sodium, and I also get milliequivalents of chloride. All right? It provides both of those. Okay? So let's do the same thing for sodium acetate. And I'll try to speed up here for the sake of your sanity. It works all the same. Sodium acetate provides 1 sodium and 1 acetate. So how many milliosmoles? 2 particles for every millimole. And again, since it's 1 to 1 all the way across, and the valence on sodium is 1, the valence on acetate is 1, again, once you just multiply across with the millimoles, you get the same values. I'll spare you potassium chloride works the same way. The little trick I'll just point out here was calcium chloride. You guys have struggled with calcium chloride. Let's convert its weight here, and again, we're starting with this weight of calcium chloride. To get to the number of molecules, we'll divide by its molecular weight. So here we are, 2.25 millimoles. Calcium chloride, how many milliosmoles? Calcium plus chloride plus chloride. CaCl2 has 3 particles, that's 3 milliosmoles per molecule, so that's why I multiplied that by 3. Also, be careful here. Now I take the milliosmoles, while it's 1 to 1 here, the valence on calcium is 2, so that's where the 2 comes from. Be careful here, the valence on chloride is still 1, but there are 2 millimoles for every one of those molecules. So again, in the end, you get those values. So, and again, you'll download this stuff. Just remember, you have to add it all up. You'll notice after you're done with all of that, I had to add the sodium from the sodium chloride plus the sodium acetate to get the total sodium. And chloride had chloride from all of those things. So you add those all up and do all of that, and there you're done. So